Hello everybody, welcome back. So the goal for today, this recording, is essentially to do a video version of the gist for today. And so I would like to do an example of finding and classifying the critical numbers of this function right here, f of x equals this big polynomial. Now, for the record, when someone says classify a critical number, they mean tell me whether that critical number corresponds to a local minimum of the function, resembling something like this, maybe a parabola opening up, or maybe an absolute value opening up at that location. Does it correspond to a local maximum, where the graph resembles a parabola opening down, or an absolute value function opening down? Or perhaps is neither of those the case? Do you maybe have a critical number where the graph flattens off? Should do that more carefully. Let's try it again. Where the graph flattens off at the critical number but does not become a local min or a local max. And there are really two primary ways that this can happen. Either your function resembles x cubed and goes from increasing to increasing, or your function resembles negative x cubed, going from decreasing to decreasing. Tell me what is going on at each of the critical numbers of this function. Now, this process begins, of course, by finding out what those critical numbers even are. So let's go ahead and calculate the first derivative of this function using the power rule all the way through. X cubed minus 7x squared plus 15x minus 9, and the derivative of 2 vanishes. And this factors, I think you can do this by grouping. No, you can't. I think you would have to use probably rational root theorem to factor this, but I'll go ahead and give you the factorization. X minus 1 x minus 3 quantity squared is how this derivative factors. Now the first derivative is defined at every value of x. So to find the critical numbers, let's set this equal to 0, and the critical numbers are x equals 1 and x equals 3. Now, when it comes to classifying these critical numbers, there are typically two tools which are used to do that, which can be really fast once you get into the habit of using them. And that's the first and second derivative test. Now, despite the name, I find that students tend to gravitate more toward using the second derivative test first. And the idea behind the second derivative test is this. It says, okay, look at these drawings that we made when we were talking about local mins and local maxes. Oftentimes, if you have a local min, then the graph will resemble a parabola that opens up at that location. So the graph will be concave up at a local min. And conversely, the graph will be concave down at a local max. So the second derivative test says, hey, if your second derivative is positive, so that your function is concave up, your critical point corresponds to the bottom of a valley, then it corresponds to a local minimum. If your function is concave down, and your graph resembles a parabola opening down, your critical number corresponds to a local max. So let's go ahead and try the second derivative test on this function and its critical numbers. So let's go ahead and find the second derivative, and by virtue of power rule, this is going to be f double prime of x equals, let's see, the 3 comes down off x cubed. Alright, here we go. 3x squared minus 14x plus 15. And if I plug in the first critical number of 1, I get 3 take away 14 plus 15, which is certainly some positive number, whatever it happens to be. Since the second derivative is positive, the function is concave up in the vicinity of x equals 1. And because of that, x equals 1 is a local min. And I do find it helpful just to draw this little sketch on the side here, because it helps me to remember that a positive second derivative is a local min. Gives you a local min, which is a little bit opposite, I think, of what most folks expect to happen. If I try the same thing on x equals 3, though, 3 times 9 minus 14 times 3 plus 15, this quantity works out to be exactly 0. And that's a bit of a problem, because the second derivative test doesn't tell me anything about what's going on at f double prime equals 0. If you have a critical number and f double prime equals 0, anything could happen. Anything could happen. You could have a local minimum, you could have a local maximum, or neither could be the case. You really have no idea what's going on here. Second derivative test tells you nothing. So that means that if I want to classify x equals 3 as either a local min, a local max, or neither, I will have to use a different test. And that's where the first derivative test comes in. And this is usually, as I said, a little bit opposite for students, where they will tend to use the first derivative test second as sort of a last resort. Now the idea is this. We have these sort of quintessential shapes here, corresponding to local min, local max, or neither. And the idea is to look at what the first derivative is doing in the vicinity of your critical number. It could be that your first derivative is changing from positive to negative as you pass over that critical number. So the original function is going from increasing to decreasing, and your critical number corresponds to a local max. Or it could be that your first derivative changes from negative to positive. So the original function changes from decreasing to increasing, and your critical number corresponds to a local min. But it could also be the case that your first derivative does not change sign as you pass across the critical number. It's either positive on the left and the right, or negative on the left and the right. And so in these two cases, your critical number is neither a local min nor a local max. So here's what I will often see folks do just to keep themselves organized. They'll get a little chart going, and on the chart, they will list first all the critical numbers that they found, 1 and 3. And maybe we'll make a little mark here that these two numbers were critical numbers because they made the first derivative 0. The idea now is to pick two test values of x nearby 3. So I can pick 2, for example, and 4, because 2 is not past 1. It's between 1 and 3. Now if I plug that into f prime, then the result of this is a positive number. And if I plug my other test value 4, the result of this is also positive. So this function in the neighborhood of 3 resembles this situation, where the original function is increasing to the left and increasing to the right of x equals 3. And so based on that, I can conclude that x equals 3 is neither a local min nor a local max.